Now let's go to electrolysis. Now, from the way the words are written, there are two words that make up electrolysis. Electro meaning electricity or electrical, then lysis meaning splitting or breaking down something. Now, electrolysis means the splitting or chemical breakdown of a compound into its positive and negative ions by passage of direct current through its molten or aqueous solution. Electrolysis is the splitting. Electrolysis is the splitting of a chemical compound into its component ions. That's positive ions and negative ions by passage of direct current through its molten or aqueous state. That means, for electrolysis to occur in a compound, it must either be dissolved in water or be melted into a liquid. We'll get to that in a jiffy. So take note of this definition. Molten state means that a substance is melted into liquid from solid state. And aqueous state means a substance is, in a state of being dissolved in water. That's what we call aqueous or aqueous state. So let's go ahead and look at an electrolytic cell. Now, take for example, you have an electrolytic cell like this with rods dipped into the cell. These rods are called, the two rods are called what? They are called electrodes. It is the rods that, bring electrical energy or conduct electricity from the cell or from the source of direct current into the solution or the molten state of the electrolyte. This is the liquid called the electrolyte. It is this liquid that is called the electrolyte. That's the substance that we want to use electrolysis to split. Let me identify some more parts. This is called the electrolytic pot. This is the electrolytic pot. This is called the electrolytic pot. This is sometimes called altogether. This is sometimes called a VOLTAIC cell. So, what else? Okay, now, whenever this happens, let's take the electrolysis of, sodium chloride, for example. Let's take the electrolysis of sodium chloride, for example, molten sodium chloride. Molten sodium chloride. When I say molten sodium chloride, okay, let me now explain what I mean by molten. When we say molten sodium chloride, we mean sodium chloride that's in solid form and now heated to become sodium chloride in liquid form. That's now been heated to become sodium chloride in liquid form. In this case, there are two ions. When sodium chloride is in solid form, there will be no ions at all because it will not dissociate. But when you heat it and it melts into liquid, it will produce two ions. Cation, the cation produced will be what? Na+. It will dissociate to give you Na+ and what? And dissociate to give you Cl- as the anion. So it will dissociate to give Na+ and Cl-. That's in the molten state. This will happen in the what? In the molten state. When sodium chloride is in the molten state, there will be two ions present, Na+ and Cl-. Let's now look at what happens when sodium chloride is in the aqueous state. Now, instead of heating sodium chloride, you could also take the sodium chloride, the white crystalline solid, and what? And dissolve it in water. So, if you do that, if you take the white crystalline solid and dissolve it in water, what do you get? You don't get molten sodium chloride. You now get aqueous sodium chloride because the white crystalline solid will disappear into the water in form of what? NaCl dot H2O, aqueous. So in that case, your sodium chloride, in that case, your sodium chloride dissociates into what? Into Cl minus and Na plus. But don't forget, water is also present. And in this aqueous solution, water too will be ionized and it will dissociate into what? H plus and OH minus. So when sodium chloride is dissolved in water, you get 4 different ions. What are the ions? You get 2 anions and you get what? 2 cations. Let's put it this way. You get what? 2 anions. The anions you get are Cl minus from sodium chloride and OH minus from water. You also get 2 cations. The cations you get are what? Na plus from sodium chloride and what? H plus from water. So that's just the difference. In the molten state, you get only Cl minus and Na plus because water is not present. You are only melting sodium chloride into liquid form. But in the aqueous state, you have dissolved the sodium chloride in water, so there will be 4 ions present. 2 from water, 2 from what? Sodium chloride itself. So you will have, that means you will have chloride ion and hydroxide ion present in the electrolyte, and you will have Na plus and H plus present in the electrolyte. Is that clear? Let's continue. Now, if this was to happen, let's just pick anyone. Let's just pick sodium. Let's say our electrolyte is molten sodium chloride, NaCl minus. Now, when you have that sodium chloride, when you have that electrolyte, that molten sodium chloride electrolyte inside the voltaic cell like this, each of the ions can go in any direction. Sodium can come here. Some sodium ions will move in this direction. Some will move in this direction. They can move in any direction they like. So the direction is, delocalized. We call this movement delocalized movement of ions. They can move towards any electrode in any direction. You understand? They move randomly in every direction when this cell is still like this. But something happens once you connect. A different thing happens once you connect the cell to an external source of electricity. Let me put it this way. So let's now assume that you connect the electrodes. Let's assume that you connect, never mind that my electrodes are not very straight. I'm using my hand. You use your ruler to draw yours. Now, let's now assume that you connect the electrodes to an external source of current like this. Let's say you place a battery here and you connect the electrodes to it. You now have your electrolyte is now, your electrolyte is now what? Connected to an external source of electrical energy. So in this case now, when the electrodes are connected to an external source of electricity, which is a DC source, that DC source has 2 parts. Let me draw it in a way you will remember. The DC source has 2 parts. It's going to have the positive pointed mouth and the what? It's going to have the positive pointed mouth and the flat. It's going to have this positive pointed mouth and the what? The flat. So this is the flat, second side. This is the positive, this is the negative. Remember this as your what? Remember this as your, what do we call it? As your tiger cell. Once you do this to the electrolytic cell, the electrons will not move in non-directional fashion anymore. Let's clean this. The electrons will not move in non-directional fashion anymore because the electrodes are now labeled. This is now the electrode connected to the positive terminal of the battery is called the positive electrode, while the one connected to the negative terminal of the battery is called what? The negative electrode. So this is now your cathode. This is called the cathode here, while this is called what? The what? The anode. Excuse me. I think I'm losing my notes here, sorry. One second, let me pull it back up. Okay, let's continue. This is called the cathode here. This is called the anode. This is called the anode. So there's a short trick that we always use in electrolysis. Anions drift towards the anode. Anions what? Drift towards the anode. Take note of that concept. And cations drift towards the what? The cathode. Anions drift towards the anode and cations drift towards the cathode. So the non-directional delocalized movement will stop once the electrodes are connected to terminals of a battery. So that means in this case now, what will happen is that sodium ions, Na plus ions, will now move towards the cathode. Sodium ions will all now drift towards the what? The cathode. While chloride ions, from wherever they are, chloride ions will drift towards the what? The anode. All chloride ions will be drifting towards the anode. So there will now be directional movement. After connection of the electrodes to a cell or to a DC source, there will be directional movement. And that's what we call electrolysis. That way, the different parts of the compound can be separated. And that's what we call electrolysis. Now, let's go to some basic meanings. Electrodes. So from what I've explained now, what we call electrodes? Electrodes are conductors. They are conductors carrying electricity. They are conductors carrying electricity into an electrolyte. Electrodes are conductors carrying electricity into an electrolyte. They may be metals. They may be what? They may be metals, e.g. They may be metals, e.g. Zinc, platinum. Depending on the kind of electrolysis you are doing, there are many different types of electrodes we use. Zinc, platinum, copper, or non-metals. They may be non-metals. The electrodes may be non-metals, e.g. carbon, graphite, e.g. graphite, etc. Some non-metals are used as electrodes too. Let's define another, important thing in electrolysis, the electrolytes. Electrodes are usually in form of rods. Take note of that too. The electrolytes. Electrolytes are these are molten. They are either melted, solid substances, or solid substances dissolved in water. So we call them, these are molten or aqueous. These are molten or aqueous. These are molten or aqueous solutions. These are molten or aqueous solutions. These are molten or aqueous solutions of acids, bases. They are usually molten or aqueous solutions of acids, bases, and salt or salt. Let's use it that way. Or salt. You understand? Electrolytes are mostly ionic substances. Electrolytes are mostly ionic substances. And there are types of electrolytes. There are different types of electrolytes. There are different types of electrolytes. Let's just, you understand? Take a short note. There are different types of electrolytes. There are strong electrolytes. There are strong electrolytes. And there are what? Weak electrolytes. There are strong electrolytes, and let me not do this twice. Let's just leave a space so I can put the examples underneath each one. There are strong electrolytes and there are weak electrolytes. So, strong electrolytes, what are they? And what are weak electrolytes? We'll take that one after the other now. Strong electrolytes are, electrolytes. They are electrolytes which ionize. Electrolytes which ionize completely in solution. Usually they are strong acids, bases, or very strongly ionic substances. HCl, NaOH, H2SO4, NaOH, H2SO4, etc. While weak electrolytes are electrolytes which ionize. These are weak electrolytes are electrolytes which ionize. Electrolytes which ionize incompletely. Electrolytes which ionize incompletely in solution. There are many examples too. Aqueous ammonia NH3.H2O, which is often written as NH3 aqueous. Aqueous ammonia is a weak electrolyte. CH3COOH is also a weak electrolyte. That's acetic acid. H2CO3, triazocarbonate 4 acid, is a weak electrolyte. H3PO4 is a weak electrolyte, and so on and so forth. So those are weak electrolytes, substances that ionize only slightly in solution. Now let's go to examples of electrolysis. Examples of what? Electrolysis. Let's take some examples of electrolysis. Okay, or let's not take this first. Let's take factors affecting the discharge of ions in electrolysis. Let's do that first. Factors affecting the what? The discharge of of ions in electrolysis. Factors affecting the discharge of ions in electrolysis. Now, as we mentioned earlier, that in some electrolysis, you have up to 2 ions drifting towards the same electrode. So number 1 is preferential discharge, or let's say position of ion in the activity, position of ions in the activity series. That's number 1. Number 2, number 1, position of ion in the activity series. Number 2, nature of the electrodes. Nature of the electrodes. The type of electrodes used in an electrolysis can also affect the ions discharged in that electrolysis. So take note of the nature of the ions and concentration. Nature of the electrodes used and concentration of what? Of ions. Concentration of ions. This affects anions. Let's put it there. This affects anions mostly. So let's take them one by one. Let's pause here for now, and we'll continue in the next video.